Hello friends, this is me S.Dinesh Kumar from DSD Department. This is my digital system design project. This is the truth table and the circuit for the AND gate. When we give both the inputs as 0 and the AND gate output as 0, which is shown in the form of a bulb in the circuit which is switched off. If we give one input as 1 and another input as 0, it will show the output as 0, which as shown in the bulb is switched off. Then we give one input as 0 and the other input as 1. Again it will show the same output as 0 and the bulb which is switched off. At last, when we give both the input as 1, its output is 1, which shows the glowing the bulb which is switched on. Now let's see about the NAND gate. Usually a NAND gate is the inverse of an AND gate. For example, in an AND gate, if the input both are 0, the output will be also a 0. But in the case of NAND gate, if we give both the input as 0, the output will be 1. In the case of NAND gate, if we give any input as 1, you will receive the output as 0. But in the case of NAND gate, if you put any one of the input as 1, you will get the output as 1. It does not matter on the both sides. If we give both the input as 1, you receive the output as 0 in the case of NAND gate. In previous case, we seen about 2 input NAND gate. Now let's see about 3 input NAND gate. This is also an usual inverse type of AND gate. In 2 input case we use 2 input. In this case we are using 3 input, such as input 1 and 2 and 3. Now let's see the experimental values for the truth table. If we give 3 inputs as 0, the output always will be 1. If we give one input as 1 and the other inputs as 0, we will get the output as 1. And the first is 0, and next second input as 1, third input as 0, we will get the output as 1. And we put the last input as 1 and the second input as 1, we will get the output as 1. And we provide the last input as 1 and the other both are 0 in the input, and we will receive the output as 1. And we will put the first one as 1 and the last one as 1, we will get the output as 1. And we will put the first one as 1, second one as 1, third one as 1, we will get the output as 0. And all the inputs as 1, the output will be 0 in 3 input NAND gate. Now let's see about the NOT gate, and this is the layout of the NOT gate or the logic diagram of the NOT gate. Its usual function is to give the inverse of the input always. For example, if we give 0 as input, it gives the output as 1, or if we give input as 1, it will give outputs as 0. Now let's see about the OR gate. This is the logic diagram of the NOR gate. Let's see it. Its components are 2 inputs as represented by the 2 switches, and through the OR gate the output represented as the electric bulb. Let's see the truth table for the OR gate. If we give both the input as 0, the output shows as 0 as we see the bulb is switched off. If we provide one input as 1 and the output as 1, which is the bulb is glowing. If we switch it to A equal to 1 and B equal to 0, the output shows 1, which the bulb is glowing. If we give both input as 0, higher one, we receive the same output, which the bulb is glowing, and it is switched on. Now let's see about the NOR gate. Actually, NOR gate is the inverse of the OR gate. That is, if we give 2 input as 0, the NOR gate gives output as 1. But in the case of OR gate, when we give both the inputs as 0, the output will be usually 0. If we give any input as 1, the NOR gate depicts the output as 0. But in the case of OR gate, if we give any input as 1, the output is 1. If we give both the input as 1, the output always be 0. But in the case of OR gate, when both the inputs as 1, the output always be 1. Now let's see about the XOR gate, and this is the usual logical expression of the XOR gate, which consists two inputs as switches and one output as bulb and middle the XOR gate. And its usual formula is A complement B plus AB complement. Now let's see the experimental values for the truth table. If we give the both input as 1, the output will be 0. If we give either one input as 0, either this one or this one, you receive the same output as 1. If we give both the input as 0, we will not receive an output as 1 and the output is 0. This is the representation of the full adder. Usually the full adder made up of two half adders. As you can see here, here is an full half adder and here is the another half adder, and the components of the full adder are three switches and represented as A, B, C, N, and two XOR gates, two AND gates, one OR gate, and two outputs is represented as S and C out. Now we can try the truth table using this experiment for the full adder. If we give all the inputs as 0, we won't receive any output, that is both the outputs will be 0. That is A as 0, B as 0 and C in as 0 and C as 1, and we get the output as 1 in S. If we put A and C as 0 and B as 1, and we receive the output as the same sum as 1 and the carrier 0. When we put A equal to 0 and B and C are 1, we will receive the output as the C out, that is carry. And we put A is equal to 1 and B and C are 0, and we will receive the output as sum equal to 1. And we will put A and C equal to 1, we will get the output in C out as 1, while other the sum is equal to 0. When we put A and B equal to 1 and C as 0, we will receive the output as carry C equal to 1. When we get all the input as equal to 1, we will get the output both S and C out are equal to 1. S and C out equal to 1. Now let's see about half adder. Usually the half adder consists of OR gate and AND gate. Here the half adder is connected with the two input of A and B. From the same two inputs, the AND gate is also connected. The OR gate of the output connected with the which is represented by the sum, while B input is connected to the AND gate, and the output from the AND gate is known as C or carry. And now let's check the truth table for this experiment. If we give both the inputs as 0, we won't receive any outputs, both the sum as well as carry. But we give any input as 1. For example, we give A as 1, we will receive the output as the sum as 1. Or we give B as 1, we will receive the same output, that is in the sum, as 1. You can see here. When give the both the inputs as 1, therefore A equal to 1, B equal to 1, we will receive the output in the carry, as you can see here. This is the usual representation of the half subtractor. The difference between the half adder and the half subtractor is of this NOR gate. Now let's try the truth table for the half subtractor. If we give the both input as 0, the output is 0 in both the difference and borrow. In previous case, the half adder consists of two outputs named as sum and carry, but now both the outputs as named as difference and borrow respectively. Now if we give the first input as 1 in A and the second one as 0 in B, then we receive the output as 1 in D difference and the borrow as 0. If we give the second input as 1 and first input as 0, we receive the output as 1 and 1 in the both difference and borrow. If we give both the input as 1, we don't get any output in both difference and borrow. This is the representation of the full subtractor, and difference between the full adder and the full subtractor is the presence of the NOR gate in between the two half adders. Then the components of the full subtractor is 3 outputs A, B and C in, and the presence of 2 OR gates and 2 AND gates, 2 NOR gate, 1 OR gate, and the output is represented as differentiate and C out, and the C represented as the C borrow. Then let's check out the truth table for the experiment. At first we give all the inputs as 0. Then as usual the output will be 0 on difference as well as the C out or C borrow. If we give C in, that is the third input, as 1, you get the output as both difference and C out borrow. Then if we give A and C are 0 and switching on B is equal to 1, we will receive the output both on the difference and the C out. Then we give A as 0 and both B and C are equal to 1. Then we will receive the only output on the C out, that is borrow. Then if we only put the A is equal to 1 and B and C are equal to 0, we will get the output as the difference. Then if we give A and C are equal to 1, then the remaining input as 0, we won't receive any output in the difference or C out, as you can see here. Then if we give B equal to 0 and last equal to 0, B equal to 1, here also we won't receive any output on difference and C out, same as the previous case. But we will give all the input are equal to 1, we will get both the input as equal to 1. Let us are going to see the code converter part 1. In part 1 we can see the code converter of binary to gray as well as gray to binary. So this is the converter of binary code to gray code, and its components are 4 inputs such as named as B1, B2, B3, B4 respectively, and 3 XOR gates and 4 outputs which are connected with the bulbs and named as G1, G2, G3, G4 respectively. And these converters are used to convert the binary code to gray code and vice versa to the gray code to the binary code converters. And we can explain the circuit diagram. Let's example binary code value 3. The values are 003 for 1. To get an output for 3, switch it on B3 and B4. Then the G3 will light up. Then this is the value for respective gray code number 3. Similarly, for binary code 7, we can enter the inputs as 0, 111 by entering 0 in B1 and 1 in B2, B3, B4 respectively. And we can see the respective gray code value for binary code values 7. Similarly, we can see it for gray code to binary code converters, and it is used to convert the gray code to binary code values respectively. And we are going to see about code converter type 2. In this type 2 we are going to cover conversion of BCD to XS3 code as well as XS3 code to BCD. First we are going to see about BCD code to XS3 code type converter. As usual, its component are 4 input which is represented by A, B, C, D respectively, and the output represented by W, X, Y, Z respectively. And the IC we are used here of AND gate, OR gate, not get, and the connections are made about in the diagram. And now we are going to check where it is working or not by using some examples. Let's take the binary code value. Let's take 6. Its binary code value is 0, 1, 1 and 0. A0, B1, C1, D0 as the procedure, and it is the value for decimal number 6 for the output W and Z. Another example, let's take binary code value number 10. For 10, the binary code value is 1, 0, 1, 0, and it's displaying the respective XS3 code for the binary code number 10. And similarly, we can see the respective binary code values and respective XS3 values by using the XS3 to the BCD conversion coders respectively. Let's see what is the multiplex and the demultiplex is. Multiplex are the electrical device generally used to get the single output from the multiple outputs, where the demultiplex are the electrical circuits used to get the multiple outputs from the single output. Single input is given. These are controlled by two electron inputs, which is named as S1 and S0 in both multiplexer and the demultiplex. Let's try the truth table of the multiplex and the demultiplex. So we give the input as 1 in the form of binary coded decimals, that is in the form of 0, 0 and 1, 0 in the multiplex. Then we open the sector input as 2, that is 1, 0. Then we will get the output as 1 equal to y, because we have the enter the value for 2 and also the selectors for 2. Therefore we receive the output for 2. Then you want the input as 4. We want to set the binary code for 4, and that is 0, 1, 0, 0, and change the selectors for binary code for 4. Then 4 is not possible. Then the selector lines are set up for only for 4. That is, this is called 4x1 multiplexer. Then whereas in the case of demultiplexer, the scenario is same. The only change in this is number of input as 1, whereas the number of output as 4. Then let's try the experimental demultiplexer. If you want the answer for binary codes for 3, you want to set the electrodes for binary codes 3, that is 1, 1. We have to turn on the input for all the things for the switches, so we have the outputs for 3. If you want the binary values 0 for the output, we want to set the binary codes selector for 0, that is 0, 0. We want to select turn on the input to receive the output as 0.